Question 13. How many kinds of NNs exist? Answer. There are many kinds of NNs by now. Nobody knows exactly how many. New ones, or at least variations of old ones, are invented every week. Below is a collection of some of the most well-known methods, not claiming to be complete. The two main kinds of learning algorithms are supervised and unsupervised. In supervised learning, the correct results, target values, desired outputs are known and are given to the NN during training so that the NN can adjust its weights to try match its outputs to the target values. After training, the NN is tested by giving it only input values, not target values, and seeing how close it comes to outputting the correct target values. In unsupervised learning, the NN is not provided with the correct results during training. Unsupervised NNs usually perform some kind of data compression, such as dimensionality reduction or clustering. Question 14. How many kinds of Kolla networks exist? Answer. Kolla is one of the most famous and prolific researchers in neurocomputing, and he has invented a variety of networks. But many people refer to Kolla networks without specifying which kind, often refers to one of the following three types of networks. VQ, vector quantization competitive networks that can be viewed as unsupervised density estimators or auto-associators. Kolla, 1995-1997. Hecht-Nielsen 1990, closely related to K-means cluster analysis. McQueen 1967, Anderberg 1973. Each competitive unit corresponds to a cluster, the center of which is called a codebook vector. Kolla's learning law is an online algorithm that finds the codebook vector closest to each training case and moves the winning codebook vector closer to the training case. SOM, self-organizing map competitive networks that provide a topological mapping from the input space to the clusters. Kolla, 1995. The SOM was inspired by the way in which various human sensory impressions are neurologically mapped into the brain such that spatial or other relations among stimuli correspond to spatial relations among the neurons. In a SOM, the neurons clusters are organized into a grid, usually two-dimensional, but sometimes one-dimensional or, rarely, three or more dimensional. The grid exists in a space that is separate from the input space. Any number of inputs may be used as long as the number of inputs is greater than the dimensionality of the grid space. A SOM tries to find clusters such that any two clusters that are close to each other in the grid space have codebook vectors close to each other in the input space. But the converse does not hold. Codebook vectors that are close to each other in the input space do not necessarily correspond to clusters that are close to each other in the grid. Another way to look at this is that a SOM tries to embed the grid in the input space such every training case is close to some codebook vector, but the grid is bent or stretched as little as possible. Yet another way to look at it is that a SOM is a discretely smooth mapping between regions in the input space and points in the grid space. The best way to understand this is to look at the pictures in Kolla, 1995, or various other NN textbooks. LVQ, Learning Vector Quantization Competitive Networks for Supervised Classification. Kolla, 1988, 1995. Ripley, 1996. Each codebook vector is assigned to one of the target classes. Each class may have one or more codebook vectors. A case is classified by finding the nearest codebook vector and assigning the case to the class corresponding to the codebook vector. Hence, LVQ is a kind of nearest neighbor rule of Kolla network, and this lack of precision can lead to confusion. The phrase Kolla network most. Question 15. How are layers counted? Answer. How to count layers is a matter of considerable dispute. Some people count layers of units, but of these people, some count the input layer and some don't. Some people count layers of weights, but I have no idea how they count skip layer connections. To avoid ambiguity, you should speak of a two-hidden layer network, not a four-layer network, as some would call it, or three-layer network, as others would call it, and if the connections follow any pattern other than fully connecting each layer to the next and to no others, you should carefully specify the connections. Question 16. What are cases and variables? Answer. A vector of values presented at one time to all the input units of a neural network is called a case. Example, pattern, sample, etc. The term case will be used in this FAQ because it is widely recognized, unambiguous, and requires less typing than the other terms. A case may include not only input values but also target values and possibly other information. A vector of values presented at different times to a single input unit is is often called an input variable or feature. To a statistician, it is a predictor, regressor, covariate, independent variable, explanatory variable, etc. or vector of target values associated with a given output unit of the network during training will be called a target variable in this FAQ. To a statistician, it is usually a response or dependent variable. Question 17. What are the population, sample, training set, design set, validation set, and test set? Answer. It is rarely useful to have a NN simply memorize a set of data, since memorization can be done much more efficiently by numerous algorithms for table lookup. Typically, you want the NN to be able to perform accurately on new data, that is, to generalize. There seems to be no term in the NN literature for the set of all cases that you want to be able to generalize to. Statisticians call this set the population. Sipkin, 1971, called it the grand truth distribution, but this term has never caught on. Neither is there a consistent term in the NN literature for the set of cases that are available for training and evaluating an NN. Statisticians call this set the sample. The sample is usually a subset of the population. Neurobiologists mean something entirely different by population, apparently some collection of neurons, but I have never found out the exact meaning. I am going to continue to use population in the statistical sense until NN researchers reach a consensus on some other terms for population and sample. I suspect this will never happen. Question 18. How are NNS related to statistical methods? Answer. There is considerable overlap between the fields of neural networks and statistics. Statistics is concerned with data analysis. In neural network terminology, statistical inference means learning to generalize from noisy data. Some neural networks are not concerned with data analysis. For example, those intended to model biological systems, and therefore have little to do with statistics. Some neural networks do not learn. For example, Hopfield nets, and therefore have little to do with statistics. Some neural networks can learn successfully only from noise-free data, for example, art or the perceptron rule, and therefore would not be considered statistical methods. But most neural networks that can learn to generalize effectively from noisy data are similar or identical to statistical methods. For example, feed-forward nets with no hidden layer, including functional linked neural nets and higher-order neural nets, are basically generalized linear models. Feed-forward nets with one hidden layer are closely related to projection pursuit regression. Probabilistic neural nets are identical to kernel discriminant analysis. Cohoney nets for adaptive vector quantization are very similar to k-means cluster analysis. Cohoney self-organizing maps are discrete approximations to principal curves and surfaces. HBR learning is closely related to principal component analysis. Question 19. What are combination, activation, error, and objective functions? Answer. Combination functions. Each non-input unit in a neural network combines values that are fed into it via synaptic connections from other units, producing a single value called the net input. There is no standard term in the NN literature for the function that combines values. In this FAQ, it will be called the combination function. The combination function is a vector to scalar function. Most NNs use either a linear combination function, as in MLPs, or a Euclidean distance combination function, as in RBF networks. There is a detailed discussion of networks using these two kinds of combination function under how do MLPs compare with RBFs. Activation functions. Most units in neural networks transform their net input by using a scalar-to-scalar function called an activation function, yielding a value called the unit's activation. Except possibly for output units, the activation value is fed via sympathetic connections to one or more other units. The activation function is sometimes called a transfer, and activation functions with a bounded range are often called squashing functions, such as the commonly used TANH, hyperbolic tangent, and logistic 1/1 plus expects functions. If a unit does not transform its net input, it is said to have an identity or linear activation function. The reason for using non-identity activation functions is explained under why use activation functions. Error functions. Most methods for training supervised networks require a measure of the discrepancy between the network's output value and the target desired output value. Even unsupervised networks may require such a measure of discrepancy. Question 20. What are batch, incremental, online, offline, deterministic, stochastic, adaptive, instantaneous, pattern, constructive, and sequential learning? Answer. There are many ways to categorize learning methods. The distinctions are overlapping and can be confusing, and the terminology is used very inconsistently. This answer attempts to impose some order on the chaos, probably in vain. Batch versus incremental learning, also instantaneous, pattern, and epoch. Batch learning proceeds as follows. Initialize the weights. Repeat the following steps. Process all the training data. Update the weights. Incremental learning proceeds as follows. Initialize the weights. Repeat the following steps. Process one training case. Update the weights. In the above sketches, the exact meaning of process and update depends on the particular training algorithm and can be quite complicated for methods such as Leeuwenberg-Marquardt standard backprop. See what is backprop is quite simple, though. Batch standard backprop without momentum proceeds as follows. Initialize the weights. W. Repeat the following steps. Process all the training data to compute the gradient of the average error function at W. Update the weights by subtracting the gradient times the learning rate. Question 21. What is backprop? Answer. Backprop is short for backpropagation of error. The term backpropagation causes much confusion. Strictly speaking, backpropagation refers to the method for computing the gradient of the case-wise error function with respect to the weights for a feed-forward network, a straightforward but elegant application of the chain rule of elementary calculus. Verbos 1974-1994. By extension, backpropagation or backprop refers to a training method that uses backpropagation to compute the gradient. By further extension, a backprop network is a feed-forward network trained by backpropagation. Question 22. What learning rate should be used for backprop? Answer. In standard backprop, too low a learning rate makes the network learn very slowly. Too high a learning rate makes the weights and objective function diverge, so there is no learning at all. If the objective function is quadratic, as in linear models, good learning rates can be computed from the Hessian matrix. Burt-Skars and Tsitsikris, 1996. If the objective function has many local and global optima, as in typical feed-forward ends with hidden units, the optimal learning rate often changes dramatically during the training process. Since the Hessian also changes dramatically, trying to train a NN using a constant learning rate is usually a tedious process requiring much trial and error. Question 23. What are conjugate gradients, Leeuwenberg-Marquardt, etc.? Answer. Training a neural network is, in most cases, an exercise in numerical optimization of a usually nonlinear objective function. Objective function means whatever function you are trying to optimize and is a slightly more general term than error function in that it may include other quantities such as penalties for weight decay. Methods of nonlinear optimization have been studied for hundreds of years, and there is a huge literature on the subject in fields such as numerical analysis, operations research, and statistical computing. For example, Burt-Skars, 1995, Burt-Skars and Tsitsikris, 1996, Fletcher, 1987, and Gill, Murray, and Wright, 1981, Masters, 1995, has a good elementary discussion of conjugate gradient and Leeuwenberg-Marquardt algorithms in the context of NNs. Question 24. How does ill conditioning affect NN training? Answer. Numerical condition is one of the most fundamental and important concepts in numerical analysis. Numerical condition affects the speed and accuracy of most numerical algorithms. Numerical condition is especially important in the study of neural networks because ill conditioning is a common cause of slow and inaccurate results from backprop type algorithms.